All right, ladies and gentlemen, so in this problem, we are going to solve a quadratic equation. And I have worked this out already before. And, well, let me put it this way. I've stuck it into Wolfram already, okay? I didn't really work it. And I saw that it had complex roots. So we're going to have to work with this using a technique called completing the square. The alternative technique is just to plug the thing into the quadratic equation, which just is, it's just unimaginative. I don't know. So I want to show you this method of completing the square. Of course, you could always use the quadratic equation, but that's not what I'm trying to teach you here. So if you had to solve by completing the square, here's how you would do it. First, we need to get rid of this 1. All right, so we'll get rid of the 1 and move it over to the right side. So you can't have anything but these first two values here when you're completing the square on the left side. So there, my first little move in the chess game is to get rid of that 1 on the left side. Okay, so over here I've got -1. All right, let me rewrite this real quick. 3x squared plus 2x equals -1. Now, you can't have a leading coefficient when you're completing the square, so you have to divide everything by that leading coefficient. Every term. So I'll divide every term by 3. Okay, now I've left some space here. I want to show you why. Let me rewrite this real quick. X squared plus 2/3 x. And then I'll leave that space and put equals -1/3. What we're going to do is we're going to add something to both sides, and that's the completing the square part. And so I'll tell you it, I'm going to say it to you what you have to do, and then I will demonstrate it. So what we have to do is take half the middle coefficient, square it, and add it to both sides. Let me say it again. Take half this middle coefficient, so half of 2/3, square half of 2/3, and then add that to both sides. Okay, so what is actually happening is that we have a little picture that we can draw. I just want to show this to you. Many of you have seen this before, but I had not seen it before I started teaching this subject, that there had existed a visual representation. So, you know, if you've already seen this visual, then I'm kind of wondering if you need to be watching this video or not. But if you haven't, I'll explain what's going on. So we have a square, and then next to it we always draw a little picture of a rectangle. And this is not drawn to scale by any means, all right? Okay, so this side length is x, and this side length is x. Okay, the area of this square, length times width, is x squared. And that corresponds to this first term here. So now let's look over at this term. So we're thinking about like algebra tiles. I've got x squared plus 2/3 x. Well, this side length is equivalent to this side length. So this side length here is x. And this shorter width here of this little rectangle is 2/3. Okay. So we'll just draw that in there. And so the whole area of this little rectangle here is 2/3 x, length times width. So I have x squared plus 2/3 x, okay? Now I said take half the middle coefficient. So half the middle coefficient would be 1/2 times 2/3. Okay, so here's 2/3. And we're going to cut that in half by multiplying it by 1/2. and that gives me 2 over 6, which reduces to 1 over 3. So that's half the middle coefficient. Half of 2/3 is 1/3, right? Now, that was obvious, but in some problems it's not, okay? So now, what we need to do is redraw this shape, okay? Because what I've just done is I have taken some scissors and I've cut this in half. Right, so what I'm going to do is cut this in half, and I'm going to move this new little rectangle down underneath here. So let me redraw this, and this seems tedious, and it is, but it's kind of cool when you see it the first time. After that, you'll probably just want to follow the algorithm of taking half the middle coefficient and squaring it. But the first time you see it, it's kind of neat. It really helped me understand just what was going on when we did this whole thing called completing the square. And you know, I'm going to be honest with you, all through high school and college, and even into graduate school, as I was doing this, I never did ever understand that what was happening. Okay, so now I'll draw this little piece. So this is going to be a smaller rectangle with one side length that is x and one side length that is 1/3. Right? Just taking my time here. Now down here, I'm going to move the other half of this rectangle that I cut in half. That's half the middle coefficient. Okay, so this is going to look like this. Just eyeballing it. All right. So let's label this out so you can kind of see what I've done. This is still x, and this is still x, and this side length is still x, and this side length is also x. Everything here so far is x. This little piece has a width of 1/3, right? That's half the middle coefficient, and this little width is also 1/3, which is half the middle coefficient. Now to complete the square, all we need to do is find the area of this missing little square piece. Okay? I need to find the area of that. Now the area of this little missing piece is going to be 1/3 times 1/3. So this is the square of half the middle coefficient. So half the middle coefficient was 1/3, and now we're going to square 1/3. So I need to take 1/3 squared because that's a width of 1/3 and a length of 1/3. The area would be 1/3 times 1/3. So let me just square this. Okay, we distribute that square, so 1 squared is 1, and 3 squared is 9. So the square of half the middle coefficient, which was 2/3, the square of half of 2/3 is, and I just wrote 1/3. I meant to write 1/9. Okay, 1/9. So that's what we're going to add to both sides. We'll add 1/9 to both sides. Okay. So let's simplify over here, and then we'll talk about this part. So over here on the right, I have negative 3/9 plus 1/9, which gives me negative 2/9. Okie dokie. And then I'll just rewrite this. X squared plus 2/3 x plus 1/9. Okay, so this is the state of the equation, right? Now what? Well, the beauty of doing this, completing this square, is that on the left side, you can now rewrite this as the sum or difference of two squares. So here, you do it like this. And the way that this works is it's going to be x plus and x plus. Now what goes right here is just half that middle coefficient. So half of 2/3, all right? Half of 2/3 was 2/6, which reduced to 1/3. So we just put 1/3. Okay, and that equals -2/9. Right, now you can rewrite this as the sum of two squares. So I can write this as, and I think I'm using that terminology wrong. You can just rewrite this as this binomial x plus 1/3 squared. Okay, it's not really the sum of two squares. It's just x plus 1/3 squared. So that is equal to -2/9. Now to get rid of this square here, we can square root both sides of our equation, right? Come in here and draw this bar and this bar right here. So by taking the square root of the left side, I strip away that parentheses in the square, and I just have x plus 1/3 equals the square root of -2/9. Okay, so that ends up looking like this. The square root of -2/9 is plus or minus the square root of -2 over the square root of +9. Okay, so now notice this. Let's talk about the square root of -2. So that's an irrational number. The square root of 2 is irrational, but the square root of -2 is non-real, right? So this is the square root of -2 is equal to the square root of -1 times 2. And when I have the product there under the radical, I can snap apart that radical and give each of these its own radical. So I can say the square root of -1 times the square root of 2. Okay, now the square root of -1 is the imaginary letter I. So this is equal to I times the square root of 2. That's what that is up there. And the square root of 9 is 3. So let's come back down from our side work here and kind of write this out. X plus 1/3 is equal to plus or minus, remember there's going to be two solutions here, plus or minus, up on top I'm going to write square root 2 I, and then on the bottom I'm going to write 3. Okay, so now I can subtract 1/3 from both sides in order to get x by itself. And so now I have x equals -1/3 plus or minus the square root of 2 times I over 3. It's actually possible to combine these together now. So let's just do this one more time. X equals -1 plus the square root of 2 times I, okay, over 3. And x equals -1 minus the square root of 2 times I over 3. These are the two solutions to the quadratic equation. Now, if you, this is x1, okay, and x2. These are the non-real, I don't want to say x-intercepts, right? Because they're not intercepting the x-axis. They're intercepting the imaginary axis at these coordinates, okay, at these points. So there's a great video out there from Welch, I think it's called Welch Labs, that's called, it's a great video series called Imaginary Numbers Are Real. That if you want to see how to visualize these imaginary solutions, you can go watch that, because the word imaginary, as they say in that video series, the word imaginary is a really bad term for what these are, because they're not fake. Like, that's what most students think it means. They're fake solutions or somehow fantastical or frivolous or throwaway. And a lot of books and a lot of homework assignments just ignore the imaginary solutions. For some reason, they think students can't handle them. Even in my Algebra 1 curriculum, I'm not instructed to teach imaginary roots like that. So I think we should, because I mean, most of the problems that you just come up with off the top of your head for quadratic equations are going to have imaginary roots. All right. Anyway, so now what? Well, it would be helpful if we could find the y-intercept and the vertex and the axis of symmetry, and we could actually graph this thing. All right. So this equation has a y-intercept at 1. Okay, it has a y-intercept at 1. So we've got our solutions here. Let me put these in a box. All right. And so I have my y-intercept at 1. And the way that you would find that y-intercept is, I mean, in a quadratic equation, it's always this last term. That's the c term. Because, you know, what we're really, when I'm talking about the c term, I'm saying that this is ax squared plus bx plus c. This is the standard form of a quadratic equation. And so this c value right here, that's the y-intercept. So 1. So down here I'll write, I don't know, right here, y-int equals 0, 1. Okay? And how about the vertex? Well, the vertex and the axis of symmetry go hand in hand, because the x value of that vertex is the axis of symmetry. So the way that we would find the x value of the axis of symmetry is to use this cool little formula here. So the x value of the vertex is equal to negative b over 2 times a. So that really requires you to know what those a and b values are. So b is 2 and a is 3. So we go over here and say that x is equal to negative 2 over 2 times 3, because a was 3. All right, well, 2 times 3 is 6, so it's negative 2 over 6, which is negative 1/3. All right, which is 0.3 repeating if you're a decimal person. Now, we found the x value. What about the y value? Now, I really think that it's important that students know how to evaluate quadratic equations by hand. Okay, so don't reach for this guy here. Try to do it by hand. And so what we need to do is evaluate 3x squared plus 2x plus 1 at negative 1/3. So let me just write this. What we're doing is we're evaluating the quadratic function at negative 1/3. That's how you want to look at it. So that's equal to 3 times negative 1/3 squared. And then it's plus 2 times negative 1/3. Okay, plus 1. So this is the x value of the vertex. This is also the axis of symmetry. And now we're going to find the y value of the vertex. That's f of negative 1/3. So when x is negative 1/3, what is y? That's what we're finding right now. So that's equal to 3 over, let's see, 3 times 1/9 minus 2/3 plus 1. Okay, so this is equal to 3/9, which is really just 1/3. So 1/3 minus 2/3 plus 3/3. That'll give me the y value of the vertex. So here we've got 1/3 minus 2/3 plus 3/3. We go from left to right. So 1/3 minus 2/3 is negative 1/3. All right. Plus 3/3 is back to 2/3. So here we are at 2/3. All right. So that's equal to 0.6 repeating. So the vertex, and we should indicate if this is a minimum or a maximum. What you do is look at the A value and see if it's positive or negative. It's positive, so this is going to be a minimum. So this is going to be the lowest point on the quadratic graph, and that's located at negative 1/3. See, I forgot this negative sign here. Negative 1/3, comma 2/3. And this is good. I'm glad that it's like this because what it means is that the bottom of this graph is located in quadrant 2. And we're going to, pardon me, we're going to graph it in a second. But when the bottom of the graph is not in quadrants 3 or 4, you're going to have imaginary solutions because the bottom of the hoop is above the x-axis. See, the lowest point on this graph is going to be negative 1/3, comma 2/3. So below 2/3, there's nothing there. So this never intercepts the x-axis. So it has no real solutions. I mean, just by looking at it, you already know that the solutions are imaginary. But if you wanted to test to see if there were real solutions, you could look at the vertex, and that would tell you if it was in quadrant 1 or 2, and that was the vertex point, then it has, and it's a minimum, then it has no real solutions. If it's in quadrants 3 or 4 and it's a maximum, it has no real solutions. Okay, so that's how that kind of works. So now we have to do one other thing. So we have to find the reflection of the y-intercept because we have to have another point, and I'll explain why in a moment. But let me go ahead and find that because I know I'm going to have to find it. So this is the reflection of y-int. Right? I'll explain why we need that in a second, but the way that you find it is you look at the vertex, okay, and you add this distance. So this x value says that the vertex is to the left of the y-axis by 1/3. So if I wanted to find the reflection of that y-intercept, I would just need to add 1/3 or add negative 1/3 to negative 1/3. In other words, double this. So negative 1/3 times 2 is negative 2/3. So what I'm saying is that the reflection of the y-intercept would be located at negative 2/3, comma 1. And I will prove all this to you here in a second. So this is the information I need. All right, this is everything that a teacher would ask of you. But now we can create a little graph using this information. Okay, I told you before that we're going to be working mostly in the second quadrant. So let me just work a little bit here and figure out my scale. Let me think about it for a second. Okay. Okay, this makes sense to me. This is the y-axis, and this is the x-axis. All right, here's the origin point right here. So the first thing we should graph is we should put in a scale with our tick marks here. And I know that I'm going to have to be working in these fractional areas, so I'll make everything 1/3. Okay, so each step is going to be 1/3. Give me a second here. Let me think about this. Yeah, I guess I'll make this will be 1/3, 2/3, and that'll be 1. Okay, so this is 1, this is 2/3, and this is 1/3. I'll do the same thing in the other direction. Let me go down 1/3, 2/3, and then -1. So this is -1, and this is -2/3, and this is -1/3. Now I need to do the same thing going in this direction here. Okay, 1/3, 2/3, 3/3, 4/3, 5/3. Okay, so this is -1/3, this is -2/3, and this is -1. Okay, so now we can plot in everything that we need. The y-intercept is at +1. Okay, there's that point. Now we can plot in the vertex at -1/3, 2/3, which is really easy since we delineated our graph in increments of thirds. All right, so there's the vertex of the function or of the quadratic equation. And now we need to show that reflection of the, you see, because I know that it's going to form this hoop shape, but where do I start going up this direction? Well, that's the reflection of the y-intercept. So that's at -2/3, 1. Right there. A lot of people forget to do that one. So really, this is all you need. You know you're going to be going up. So I just try to form a nice hoop shape here at the bottom. Right? And then it kind of goes up like this. You know, you're just sketching. It's not a perfect representation, but you try to mirror it. This is a bit of an artistic exercise. Okay, so there you go. Right? Yeah, more or less looks like that. It never crosses the x-axis, so it has no real solutions. Right? These are the two imaginary solutions. Now, the question is, are we correct? Well, we're going to find that, there goes my coffee pot turning off. We're going to go find that out in two different pieces of software. One of them is going to be Desmos, and the other one is going to be our Wolfram Alpha. So let me show you my screen so you can see. Here's Wolfram showing us that the result is -1/3 times I, open parentheses, square root of 2 plus -I. Okay, so it looks like what they have done is they've gotten that 3 out of the denominator, and they've just pulled it out. Okay, and then they just rearrange these terms. Okay, so that's the same thing that I wrote, only in a different form. Right? I don't really like that form. It doesn't make any sense to me why they would write it quite like that, but that's how they wrote the solutions. But if let's see if they show a graph of this thing. Why wouldn't they show a graph? Okay, let's go to Desmos and type it in. And we're going to type in here y equals 3x squared plus 2x plus 1. All right, let's see if we were right about all of our things that we got. We said that this should be 0, 1, and we said this should be negative 1/3 comma 2/3, and there it is. And so the reflection on the y-axis should be right here. Let's see if I can get it to be right on it. I don't know if I'll be able to get it right on it, but it's negative 2/3 comma 1. If you look at that, it's as close as I guess I'm going to get it, huh? Negative 2/3 comma 1. Okay. So just to prove that the thing that I wrote is equal to the thing that they wrote, we'll put in here, let's see, what have they got here? Let's see, I'm going to type what I wrote. Negative, let me put this in parentheses, negative 1 plus square root 2, well, I guess square root negative 2, okay, divided by 3. Let's see what that evaluates to. Okay, see, this is what they want to do with this. It's just weird that they want to write it this way. Okay, so let's go back to our graph, make sure that we did everything right there, and now we'll go back to our writing paper so you can kind of see a summary of everything that we did here. We found the solutions to the quadratic equation, and they were non-real. We found the y-intercept, the vertex, and we identified that as a minimum, and then we reflected the y-intercept so we could find another point to plot, and I should have plotted in the axis of symmetry, which would just be this dotted vertical line passing straight through the vertex, which is at negative 1/3. So here's your axis of symmetry. Back when I was a kid, this was all required as part of one problem. It took me 32 minutes to solve it. I'll solve it all out and check it. So it is a process, you know, and if you were assigned 5 of these in one night, you would be working for 2 hours, man, easy. So luckily it just took up that one page and we solved it using completing the square. So I'm still somewhat mystified about how they wrote this different than me, and I'll go check it out. But for now, we'll leave it there, and we'll outro on this image. So thanks so much for watching. I hope that this was of some use to you if you're having to find, if you're having to solve quadratic equations that involve non-real solutions, then maybe this video was helpful. If you had to solve quadratic equations that involved completing the square, then maybe this video was also helpful. Either way, please do like, subscribe, comment, and hit that notifications bell. Thanks.